tell Black we got a lot of people here tonight. Oh, there's Chris. Angie. Man. I thought because it's so cold that nobody would come tonight. Everybody. I'm going to take my gum out of my mouth so I can't smack it the whole time. I go back and listen to the recording and I smack the gum.
Tuesday night. My wife said they're talking about Tuesday, Wednesday.
Oh, damn. There's your telescope right there.
It's really cool, man.
Yes, it's heavier than it looks. Yes.
I didn't know you did.
I carried it with one hand in here.
It's like all the rest. You can do like 15 Oh, I still want to go with what you have, and if I don't,
We'll see.
I'll bring it back.
Yeah.
I'm going by my watch. Yeah, not with me. I had to carry a telescope in here today, so I did bring a whole box, but I have a cowbell. Sometimes I actually have to use it. We had an air horn at one time. I was told that was not appropriate. Okay, so it's 7:30 and we're going to get started. Welcome to the January meeting of the Johnson Space and Astronomical Society. I'm Doug Holland, and I'm so glad to see all of you here. A lot of people I don't know. And so before we get started, I think what we'd like to do is we'd like to greet new people. So if you're new, what you do is raise your hand and you say, tell us what your name is, how you found out about the JSC Astronomical Society, and what you're interested in astronomy. You guys right there.
Alex, I found out about this meeting mainly because of a friend who brought me here.
So the friend who brought you that nice lady over there?
Yes,
yeah, she does things like that. Okay, very good. And your other friend?
My sister.
Yeah, I'm Avery. I'm his sister, and I'm just tagging along with them.
Okay, so Avery and Alex, right?
Yes.
Okay, gotcha. We're glad you're here. Who else? First time, right there.
Brian Schneider and my son Blake Schneider and Grant Schneider. I brought Blake here when he was 11 years ago. There was an open telescope event. We hadn't been back since, and so my wife brought it up again and said, "Hey, you think about going back?" And so glad to be here.
Great. The Schneider clan is here tonight. Who else? First time here. I see a lot of new faces.
Yeah.
What? Okay, back there.
Jordan Peterson and Janelle Peterson was invited by one of the professors of University of Houston, so first time visiting.
Oh, by a professor from the University of Houston. Where is she? She's not. She left already. Okay, was it Dr. Masood by any chance?
Yes.
Oh, well, she was here, but now she's disappeared. Oh, great. Well, we're glad you're here. What was your name again?
Jordan.
Jordan.
Yes.
Okay, got the Jordan clan, the Schneider clan. All right, anybody else that wants to admit? I see Dave down here. You got to admit that this is your first time here, Dave?
Yeah.
Okay.
Happy New Year, everyone. I'm David Brown, and I've worked with Doug Holland some years ago over at JSC. This is my first time here. I've had since I was a boy in Connecticut. I've had a lifelong fascination with the stars and astronomy. So I'm excited. Rick Slater brought me. He drives a Mercedes.
I use Mercedes.
Well, Dave, we're glad you're here. We hope you come back more times. And Timothy, tell us.
Honestly, I just kind of Googled the place. I wanted to find something that I could go to. People who are interested in something similar.
And you're from Kingwood, right? Listen to that. More Kingwooders. See, we got some Kingwooders up there and some down here.
Hey.
And you're a high school student right now, is that correct? High school student right now? Or you
I'm actually UHCO.
Okay.
Just got it.
Long commute.
Well, we're glad you're here. Anyone else that wants to admit this is your first time here? Okay, you guys.
Yeah, Richard and Summer, we've actually been to your meetings, but it was way back when it was at the
Planetary Institute.
Oh, way back then.
We're both NASA contractors, so we've been to these meetings before. It's been a while.
Okay, Richard and Summer. Okay, we're glad you're here. Excellent. Phil, I can see you back there. You can't hide behind Summer. It's not going to happen. I know you're there. He's still always trying to hide from us. Okay. Oh, Dr. Masood, some of your students are here. See that? They named you while you were gone. There they are. She's glad that one of her students does. All right. Anyone else? First time here. Excellent. Very good. Okay, so here is our agenda for this evening. Not quite yet, Ronnie. Almost. If you have questions during the meeting, if you're watching us online, actually our largest audience is online. We had about 114 people last month. If you have questions during the meeting, you can send it to jscaslive@gmail.com or any of them as a YouTube comment, and Trevor will get those questions and present them to our presenters. And Trevor, thank you again for learning String. Trevor's been doing that for several years now, saved us from COVID, and he's still doing it. So we're going to have our main speaker. We're going to take a break. I'm going to tell you about the Nano VNA. I'll just put that there so you guys wonder what it is. Star Party News and have door prizes, and then go to Mod Pizza. So that's all that's on the agenda. Okay, if you would like to get on our email distribution, there's two different email distributions. The top one is for meetings only, and the bottom one is if you'd like to get all the email that we have, our total distribution. You can either take a picture of this and send your email to one of these and get on that distribution, or there's little tear-off tabs on that clipboard that's at the back. You can just tear them all off and take it with you. And I've heard from several of you that you're not getting emails. If that's true, please send us in again or contact me and we'll figure out why you guys aren't getting emails. So I'm hearing that from multiple people. Okay. Speakers. When you're up here, please use the mouse pointer here so the online audience can see what you're pointing at. Don't use a green laser pointer. And also this mic here, we've had complaints about audio online, so if you can try to stay kind of within the range of this mic, that would be good so people online can hear you. If you're way up over there, online can hear what you're saying. Alrighty. Okay. So let me introduce our main speaker. I feel like I'm forgetting something. Am I forgetting something? I don't know what it is. What?
You forgot something.
I don't know. I feel like I'm forgetting something. Whatever. Okay, so before Rodney comes up here, I want to tell you a little bit about him. Okay, Rodney Rocha continues to... hold on a second, guys. I got my glasses. All right. Rodney Rocha continues to pursue a long career as an aerospace engineer at the NASA Johnson Space Center. His specialty is Newtonian dynamics, structural dynamics, and structural vibration. He supported the early space shuttle studies, space station designs, and many other projects, including development of mathematical models of spacecraft systems and management of structural test laboratories. He currently provides engineering support to the new lunar exploration spacesuit and the current human lunar exploration programs of Artemis, Orion, and the Gateway Lunar Space Station. He has been a member of the Houston Astronomical Society, a current member of the JSC Astronomical Society, and a founding and current member of the Corpus Christi Astronomical Society, and he owns 4 telescopes. So join me in welcoming Rodney Rocha.
Thank you, Doug. Let's see. I advance this.
Just like at the return button on the.
So I got to borrow your glasses. Okay. The enter button.
Yeah. Okay. Yeah. Back.
All right. I'll try to stay close to the microphone. I'll try to, because there's people online, right?
Yeah.
Okay. I'm deliberate when I say as suggested by, because I'm going to try to make you think. I'm trying to be like Socrates, and I'll ask you questions to see what you think. Now, if you think you know everything and you want to give a long 10-minute speech, let's try to give somebody else a chance. I like speculation and people using their imagination and what they know, but anybody can participate. Some of these things I'm going to present, they really don't need resolution if it sounds funny or there's a funny result or whatever. You don't really need relativity or quantum mechanics. We don't need the Pauli exclusion principle or anything like that. So, yes, I'm proud to say that I was also a founding member when I was 13 years old in the Corpus Christi Astronomical Society, my hometown. And I just read a book then about constellations, a dipper full of stars and that Sky Observer's Guide. And I wanted to see a real telescope. And I went to the museum with my father. It was a cold winter day. And someone was taking a Newtonian homemade reflector out of their trunk. I went, they're real. They're not just pictures in books. They're real telescopes that people made and with their own hands and the mirrors. It was a beautiful telescope. And as luck would have it, there were wonderful people and mentors and adults that treated us like equals, because I met other kids my age. In 65 or so, comet Ikea Seki appeared, the giant, long, huge, long tail arcing in the sky, going to the sea base front and seeing that bright. We got up at 4 in the morning and he took us there. I thought, oh, this is what it's going to be like from now on. Every year there's a comet like this. No, I was just lucky at that time, and I thought, God, what an apparition. So lucky. All right, so for millennia, many thousands of years, or probably hundreds of thousands of years, early humans, hominids, would probably look at the sky, and they all saw them move, and it looked like there was stuff pasted on a firmament or a dome. But what are these things? And they move. Most of them are rigid. They don't change position like the stars, but two of them move a lot, the sun and the moon. And every once in a while, there's weird transient events like falling stars and comets. They didn't know what those were. But mathematics developed, the Renaissance, and there was knowledge steadily increasing. The leading natural philosophers, they didn't call themselves scientists then. That means wisdom or knowledge, but they called themselves natural philosophers. I think that's what Isaac Newton called himself. And mathematicians. They were very strong in mathematics. They knew, everyone got the idea, yeah, the Earth is kind of like a magnet pulling down iron or stuff like that. And apples fall down, rain falls down, boulders go downhill. Yeah, it's like a magnet pulling them down. But they knew about Galileo's experiments, the ramps, the little rolling balls, and the experiments he did with momentum. But maybe they called it a field or a gravitational field. And they said maybe also it explains orbits, like if you take a cord and you're whirling, tie an object to it and whirl it around. Well, that's kind of like a magnet. The gravitational field is like a cord holding it, and it's forcing it to go in a circular motion. But what propels these things? Where's the motive force in all these? But they don't explain artillery. What those strange shapes of artillery shells or cannonballs. You throw a rock in the air. Football quarterback throwing a ball. What path is that? What's going on there? Why do things slow down? Why don't they just go on forever? Or maybe people think they have to slow down. But if I'm swimming in water as hard as I can and I stop propelling myself, I slow down instantly. Why? What's that? Same with objects like a rolling cart. Unless it's going downhill, but if it's going flat, why didn't it just keep on going? Even if it just stops. How do birds stay up there? They're flat. Well, because they're flapping their wings. Well, what's that? Humans tried that later, flapping artificial wings. They didn't get anywhere. They kept falling off the bolt of the cliff. If you see those funny silent films, that's what happens. All right, but okay, the magnetic force. It's kind of like a cord pulling. It didn't explain elliptical orbits. Kepler, studying Tycho Brahe's naked eye data. There were no telescopes on Tycho Brahe in Denmark. Got all that, a mass of data, and Kepler poured through it. God, Mars is elliptical orbit. Now, he's lucky the data showed that, because Mars has a somewhat pronounced eccentric. It's out of round. It's not a circle. It's I mean, if you drew it to scale, it looks like a circle, but it was out of round. Venus is almost perfectly round, 0.007. You know, it was named after James Bond. You know, 007. So you got to be a certain age to understand what that meant. But it didn't explain that. Or but these comets coming in, they were observing with telescopes by Newton's time, and eventually they were trying to figure out their orbits. Parabolas or hyperbolas, maybe. That's not a chord. That's not an object swinging on a chord. What's going on? Is there even a theory for this? So, everyone, is there a mathematical natural law explaining these? A simple fundamental thing? Is there? There can't possibly be one explanation for all of these weird motions. They thought, well, one guy thought about it a lot. He knew what was going on. He was communicating with the other mathematicians in Europe. By the way, in one of his interviews with somebody, he said, those foreign mathematicians, he called them. He knew he was a genius. He lived to be 84, Sir Isaac Newton, and he became the leader in his old age. He was put in charge of the Mint of England. He loved that job when he was old. He became an old curmudgeon, you know, going after people. But he made his own telescope. He made a Newtonian telescope. He said, I'll make a Newtonian telescope. And I'll name it after me. It wasn't a glass mirror. It was a speculum, which is what a polished metal, a metal alloy, highly polished. We didn't get the modern materials until later, but it was the Newtonian telescope. I don't know where he ordered his diagonal from, but anyway, probably made it. I don't think Edmund Scientific existed then. You know, that's what I ordered from when I was a kid. I still have an Edmund Scientific reflector, 6-inch reflector. I bought it from a guy at NASA. I'm serious. The photography division at NASA. He said, I bought it so I could see them walk on the moon. I'm like, oh, I'm not going to break his heart. Photography division. Okay.
Dare I ask who that was?
Now, and if you didn't see them through the scope, yes.
I noticed in the picture, it has mirror moving focus, just like a Celestron does.
Oh, yeah.
You move the mirror to focus.
Yeah. It goes back and forth like this. Yeah, he couldn't order for rack and pinion from a company, so he. Well, you can see he's got a prism, so he's breaking the white light of the sun into colors. And he said, "Oh, white light is so It's spectral. It's got more colors in it than just white light. They're all mixed together." Now, if I did the experiment, I'd say the prism is doing that. It's contaminating that white light, and it's adding the colors. But he did something to prove that was not true. He put another prism in the path of it, and it went back to white light. So the prism can't be adding color and removing color at the same time. So it reverted back to white light. So I guess they're showing the ocean there because his gravitational pull and tidal forces explain why there's tides on the Earth. And other reasons, like why Europa probably has an ocean, because it's being kept warm by the distortions from its neighbor, Jupiter. So let's see. All right. 1687, he put the date on it. All is explained in mathematical precision and detail. There's the date, July 1686. So I got to correct the date there. So, Philosophiae Naturalis Principia Mathematica. The natural philosophy of the principles of mathematics. That's kind of what they call physics. Yeah. And he wrote it all in Latin. Why don't we do that today? Let's learn Latin and write everything in Latin today. Okay. So it was highly geometric. He gave geometric arguments, but the two basic things that came out of that were, let's see if I have them on this page. Newton's 3 laws of motion. I only put the third one here. They're kind of all the same, but the third one captures everything. So the first law is, does anybody remember what the first? I'm not asking the physics professor. What's the first law?
Nothing continues in motion.
An object that is in motion will tend to stay in motion unless
Right.
the force is applied.
right? If I'm moving through space freely with no forces on me and walking in a straight line, I'll do that forever until a force stops me or makes me veer from my course. Second one is actually, for every force, there's probably a reactive force. Maybe that's the third one. This is the second law. I got it wrong. This is second law. So we got to start over and come next month. I got to correct these slides. All right. So it's the second law. F equals ma. I put little arrows because when we use them, we use vector notation, meaning these quantities are not like an algebra. They're not like A plus B equals C. The numbers here are arrays of numbers, and they indicate direction, this way, that way, this way, X, Y, Z, or rotations, even. So it just means they're spatial. There's something, they have dimensions in them, X, Y, Z, and rotation sometimes. So inertia is kind of a funny thing. But if the inertia of mass could talk, it would say, I'm a measure of my resistance. I don't want to move or change the course. You got to make me. And that those are called forces. Sometimes if we want rotation, we call them moments or torques. But so it's just a measure of, I don't want to go anywhere and I don't want to change. If I'm pursuing this course, that direction at that speed, I don't want to change. And the more massive I am, the more stubborn I am about that. That's called inertia. It's not friction. That's a resistive force too, but those are bodies in contact. That's material interaction or aerodynamic drag. All right, universal law of gravitation, at least in our universe. I don't know what laws I have in the bubble universe is those other things, but an inverse square law, meaning that you're divided by something squared. The distance between the centers of two masses. So maybe that's the sun, the other one's a moon, but they could be two subatomic particles, or they could be two human beings, or whatever. It's well, how big is that force? He calculated, or he derived, or intuitively, it's the product of their masses, m1, m2, divided by the distance squared. It's kind of like how light works, the squared law. Light spreads out like that. It gets dimmer and dimmer and dimmer through a squared law. A 1 over distance squared law. The product of the masses is a property of the masses themselves, that inertia. And G is just a constant to make all the units come out right. But it's got a number. And this is kind of funny. I learned this taking astrodynamics here at this university with Dr. Blanton. G is the most poorly measured constant in physics. It's only good to, maybe you can correct me if I'm wrong over there, 4 or 5 significant figures. The other constants in physics have lots of digits. They exquisitely measured with lots of decimal places, but not G. It's hard to measure. Yes. Yes, little boy.
Why is that?
Why?
Yeah.
Well, I think it's the way you have to measure it. They put a torsion balance. This is the Egyptian cubit. No, it's a yard. Okay. I thought this is what made the pyramids. But it's not long enough. Cubit is longer than this, I think. If you put a mass here and another mass here where my fists are, and you're suspending a string, some kind of string that the torsion of it is like how many foot-pounds you have, and you put a stationary mass here like this bottle, and it's attracting this ball, so it makes it twist. Now you got to get the room, or you got to put it in a chamber, get it super, super quiet, no air currents. You can't have a tick or a flea jump on it. That'll mess it all up, No cigarette smoke blowing on it, nothing. It's got to be absolutely still. That slight pull is extremely hard to measure, that little angle. It's just hard to measure.
Okay.
The other constants of physics are, apparently they're very clever in the way they measure. It's called precision, the amount of decimal points. Now, what orbital mechanics people do is they measure GM, like GM of the sun, because it appears sometimes you get GM in the equations of motion, and they measure that. like, well, I don't really need to know the mass of the sun or the mass of the earth for something going around it. So GM is much easier to see by the way it orbits. They can do radar and tracking and all that, and it'll come out that way. All right. Oh, by the way, these are simple to write down. You could write these down on a little sheet of paper. F equals ma and the law of gravity. NASA, ESA, the Russians, anybody on Earth that really is using physics and Newtonian mechanics, we haven't changed in over 330 years. Newton, we've not modified his equations. They're exactly the same. So until we go to the speed of light or near the speed of light or near a neutron star or black hole, we don't need to change them. They'll still predict landing on Mars within 1 second or whatever. It'll get there. You know, if you know all the forces acting, including all the planets acting on that spacecraft, pulling and tugging, it can be calculated precisely. I don't know of any other science that does that where you could predict in the future what's going to happen. You know, these digital orreries that know the position of planets for 500,000 years in the future. You know, that's amazing. What other science does that? I know, but I'm not going to say it. Well, people picked up on it. They were amazed. Oh, wow. You know, Newton solved the mystery. Celestial motions are now revealed. We don't have to do superstition or supposition, or angels aren't pushing the royals around. They're actually useful. They can calculate. We can verify them by experiment. Well, one of the guys early in the 1890s was Konstantin Tsiolkovsky. So the Soviet Union commemorated him with a stamp. One of his famous sayings is the Earth. And he believed in space travel. That's what made him different. He was interested in physics, Newtonian mechanics, but he wanted humans to explore space. And one of his sayings is, even though humans were, the Earth is the cradle of mankind. And I want to update him. The Earth is the cradle of humankind, but you can't a baby cannot stay in the cradle forever. Yes, we love our beloved Earth, but there's so many, I think he meant there were so many wonders out there. Wouldn't it be wonderful to leave our cradle and go look at it, have the adventure of exploration? And he designed his own vision of space stations and spacecraft. And one of his contributions still used today for rocket design is the basic rocket equation. He even, when he derived it, he put the date 1897. You know, I finished it. Oh, here it is. Still used. Even Elon Musk uses this. But basically, what does it say? Well, it's mathematical. There's a log there, base E, and all that. It just says, if you want a velocity, you want to go real fast, I got this propellant coming out of the rocket nozzle real fast, but I want to go faster than that. I want my velocity to go faster and faster and faster. You got to carry up a lot of mass. So if you want your final velocity to be like 10 times higher or like 2.5 times higher than what it started with, I have to have 10 times the mass. That means your payload or the cargo or your human capsule is 1/10 of the whole rocket in terms of mass. You got to have, it's mostly fuel, tanks and fuel and plumbing. That's the rocket equation. You want to go fast, you got to take up a lot of fuel, and it's going to be 10 times more than your spacecraft, or even greater. Now, there's ways to make it more efficient by staging, and he thought of that too. This is one of Tsiolkovsky's designs. I think the Russians made this and put it in a museum, probably in Moscow. There he is checking on visitors that come to the museum. And it's pretty neat. He had compartments in there, living spaces and couches, and he put food and oxygen in there. He was thinking space travel, humans. And the staging rocket, he thought of that. And later it was picked up by von Braun, and of course, von Braun was German rocket scientist who learned from Hermann Oberth, who taught him, and they taught us, the Americans, you know, how to do the staging rockets. They tested that out with our captured V2s. And for those that know World War II history, we kind of captured them. You know, they surrendered to the British and Americans. They became American citizens. The Russians captured theirs. I don't know if they were willing captives or not, or the Germans that had to work for the Russians, but there was supposedly a saying at Marshall Space Flight Center in Alabama, our Germans are better than your Germans. The staging rocket is a way to make that rocket equation a little more efficient. You drop, when the stage is empty of fuel, it just drops away. And you get rid of that mass. It's dead now. And one of the ways I got into space travel, not just astronomy and interest, is watching the Walt Disney Man in Space series. And the Collier magazine and Life magazine had articles written, Missions to Mars by Werner von Braun at Peenemünde. I was in Peenemünde visiting there in 2018, went to northern Germany, Friesenland and Aurich. But we went, my wife and I said, I've got to go to Peenemünde, where the V2 rockets and V1 buzz bomber were developed. They still have some foundation buildings there and some equipment and meters, and it's a wonderful museum. And the Germans are upfront about how bad the Nazis were. But the science part was amazing. I said, I thought NASA invented that, or I thought the countdown was invented by NASA, or the blockhouse, that was NASA. No, they did it. They had the specialists in mission control. You're responsible for that system. You're go. I thought we did it all. They taught us. And Walt Disney, not only did he have wonderful stories and cartoons of American history, he loved space and was promoting von Braun. That's an early shuttle. And this is a multiple engine booster, just like Elon Musk has. Elon's is what, Super Heavy or Dragon or whatever, 33 engines on the Super Heavy. This had multiple engines too. It didn't really fly, that was a big post. Okay, I mentioned Kepler, Johannes Kepler, and he took the data from, this is before telescopes, looked at Tycho Brahe's data and enormous volumes and tons of work, and deduced that how planets really move. But here's some comets. He was intrigued by the cometary motion. They don't go around the sun right. They're weird. They come and go. They come in and disappear, whirl away. So, but when he started out, he said, I'm going to take this data and I'm going to figure it out. I'm going to prove that the divine creator of the universe is obeying or using the Mysterium Cosmographicum, the mysteries of the cosmographics. And he picked up on Euclid's, who was it? Plato, these solids. He said, the universe and the planets have to move in shells, but inside each shell is a tetrahedron, a cube, an octahedron, a dodecahedron, and something that I can't pronounce. And that's an ISO 9000 polygon. But they're within shells and shells and shells. And I know the data is going to show that. Well, he worked on it, wrecked his brain, said, it's not working out. Not working out. So I don't know how much time, I forgot, he broke his spirit, I guess. Said, okay. Then he became like a true scientist. What did the data really show? I'll just say maybe it doesn't work exactly like this. What does it really show? So he looked at it, and they're derived observational. They're called Kepler's laws, but they're by observation. He didn't use any physics or mathematics. I think you've seen these before. The orbit of a planet is an ellipse with the sun at one of the foci. So it's that squash, take a circle, squash it a little bit. It's a squash circle. That's called eccentricity. The more squashed it is, the more eccentric it is, the more it departs from a circle. And it has two foci. A circle has one in the middle. The planet's going around in a perfect circle. But when you squash it, the center splits in two foci. All right. It's amazing. You mostly use the Martian data for that. A line segment joining a planet, and the sun sweeps out equal areas in equal intervals of time. And I know everybody online can't see me do this, but it means that here's one of the ellipses, and here's another one. Pick this pink one. When it goes from here to here, take your stopwatch and measure the time. delta T, whatever. Look at this area swept out. Sweeping the area means like I have a lot of paint under my arm, and I'm sweeping the floor. I'm painting the floor. If you measure that area, then okay, that area for that time. If it's over here and this, you measure that time and say it's the same time, that's the same area. It's sweeping out. And an object in an elliptical orbit is sweeping out an elliptical, painting area in the equal amounts of time. The third one is a little more complicated. The orbital period, meaning how much time does it make to take for one revolution, beginning and it comes back to the starting point. That's called the period, how much time it is. Square it, just multiply by itself. It's proportional to the cube of the length of the semi-major axis of the orbit. For an ellipse, the semi-major axis is this long dimension. Like, take this object, here's the focus, one, here's focus, the other focus, draw a line. That length from here to here, the longest line in the ellipse, is called the major axis. But if you take half of that, it's a semi-major axis. So that's remarkable, but that's observational data. He derived this, okay, but he didn't have a law. He said, they're called laws. They're called Keplerian motion, or whatever. But Newton came along with his theory and said, these two equations, the laws, the second law of motion, F equals ma, and combined with the gravity law, which I've rewritten here in a different way. This is kind of how we use it for computing orbits. Where's my mouse? This quantity here is just a vector that for pointing. It just says it points, one object's pointing at another. But the inverse square law is here. You can rewrite these in a different way with notation. This is all calculus, but you put it into you combine the gravity law with F equals ma, which is acceleration, into what's called a differential equation. It's a balance of forces. Differential equations in calculus you're just balancing rates, the rate of this moving to the rate of this moving, the rate of this energy to the rate of this energy moving. It's kind of like algebra, but calculus and differential equations move time rates, acceleration, velocities, flux rates, the rate of change, and they're in balance in the equations. This is balancing this. So this is the standard way that they're written, and that's frequently done for the two-body problem. So you take one body, like say that's the sun, the yellow one, and the blue one is the earth, or they can be any two bodies. And I can say, well, I know they're both whirling through space, like around the galaxy and all that, but let's just say I want the sun to be standing still. I'm going to do all my observation from a sun-centered, or I'm going to look at the moon from an earth-centered. That's called a two-body problem. So you write the equations that way. And that's what I did at the lower left. When you do that, the two-body problem reveals things that Kepler would have been watering at the mouth. Remember, he tried to fit everything into the divine solids, these weird shapes and spheres. He said because the divine creator of the universe had to use geometric perfection and beauty and symmetry. Well, it turns out there is that. In a two-body problem, when you have one body and another body orbiting each other, or one's bigger than the other, and the other, you can say, pretend one of them is standing still. The shape of those orbits are completely defined or described by slicing a cone. Take this right angle cone here. If I slice it right off the top, like at the top there, just whack it off, and I take off that, where's my mouse here? My mouse. What happened to the red thing? Okay. So take that piece of the cone, I'll see a circle, right? So let me get to the microphone. If I slice at an angle, but I'm not parallel to one of the sides, I'm going to take a plane or a big knife, slice it through, but don't go parallel, don't go too steep. I get an ellipse. Take off that top segment and take it away. I'll see that what remains is an ellipse. If I now like slice it again, parallel to the side, I get a parabola. Now, you have to, this is an infinite cone. This cone has really no base. It goes on forever. It starts at that point and spreads out like a light beam or something, a light cone. Just pretend it goes on and never ends. That parabola will never end. But the circle is closed. The circle and ellipses are called closed. They come back to their starting points. The parabola does not. It keeps expanding forever. The hyperbola, you're kind of making it beyond that slope, and you can cut it different ways. It too is expanding, but it doesn't keep getting wider and wider. It actually has a limit. And you'll see it in the next year. This is another way to say it, the slicing plane. Now, if in number one, if I slice it, there's my circle. But why did somebody draw that cone above there? That cone at the upper left is not doing anything. That plane didn't cut it. Okay, let's do the ellipse. Remember, cut it at an angle, but not the steep, not to the same slope as the side of the cone. Take away that piece, there's the ellipse. Well, I still don't know what that upper cone is for. It's missing. Now I do the parabola. Remember, that's parallel to the side of the cone. And so, darn, that artist keeps drawing that other cone. What is it doing? I know with parabola. Now, when you raise it beyond upright a little bit more, the plane is cutting the two cones. I get two parabolas. That's interesting. The equations actually predict this. You know, they're called the conic sections. That equation I showed you before, you can rewrite it. Put a substitution. It goes, oh, those are the prediction of conic sections. So what Kepler would have been astounded by is the mathematics are linked to the geometry and structure of the universe. It's geometry and calculus merged together. Sometimes called analytic geometry. It's got analysis, but it's got equations, algebra, and calculus, and everything. The two are linked together, and I think Kepler would have loved that. But why two hyperbolas? Usually when the mathematics say there's two solutions, remember there's only one solution for this one, 1, 2, and 3. What would be the why? What is that saying? What is the mathematics or physics saying? Why would there be two hyperbolas possible?
There's a square.
A square? Yeah, and then when you solve it, you get two shapes. Like, so what is the one we're most interested in? Like comets that might do like that one that came in from interstellar space, Oumuamua, that long cigar-shaped object, had a highly eccentric, at the time, one of the greatest eccentricities ever discovered. So we know it came from interstellar space because it had so much speed. It's gravity at work. So it whips around.
Like, let's say this is the sun. It's coming in a lot of speed. This fifth gear is coming close around. From deep to way out there, it almost looks like a straight line. I don't know what it is like, a straight line. It almost starts curving, noticing as you reach the sun and it whips around and takes a turn, a hyperbolic turn. The sun is one of the foci, the focus. The other hyperbola is for
the force of repulsion. So you think of two protons being fired at one another at high speed. This is one of the protons. You know, photons are like charged, so they want to repel each other. It's like some magnets. So it'll approach,
come in, and take the turn in front of it. It won't go around it. It comes to the focus, the other proton will move away from it.
so that is linked. But of course, that's electromagnetism, but it's the force of repulsion. So that's why there's two hyperbolas, in case you have a force of repulsion. This is mathematics. That's an ellipse. This horizontally, that's the major axis, and up and down is the minor axis, and then there's other shapes they divide up in here, and one of them is called the latus rectum, and I'm not going to tell you what that means. You have to ask me later. And then the two-body problem does other neat things. From those two equations, and that equation I showed you, two-body problem, come a plethora of formulas. Like, man, look at all those formulas. And like, I can calculate velocity in circular orbit. It's the square root of g, remember Newton's constant, times the mass of the Earth underneath. You got a satellite or a little particle going around the Earth. If it's in a circular orbit, you just divide by the radius from the center of the Earth up to the orbit, where the orbit height or the distance from the center of the Earth, take the square root, and there it is. If I want to say I want it to escape into a parabola or hyperbola, I have to take my square root of 2 and multiply there. And no matter where you start in a circular orbit, if you multiply by the square root of 2, that's your speed for escaping. You will no longer be in an ellipse. You can go faster, of course, escape into a hyperbola if you want to, but I like that. That links it to Pythagoras, a square, if you have sides 1 on side, the square root of 2. So there's I like that algebra coming into this. And there's a parabola, which the focus is somewhere above that where it says 0. But the sides, if you keep extending this forever, they just keep getting wider and wider and wider forever. And whatever speed it had at infinity, it becomes 0 speed. In an ellipse or circle, it's an energy exchange. They don't go to 0. It's just it's going faster or slower, like an ellipse. Faster around the sun, slowing down when I get away from the sun. Faster and faster around and slowing down. For a hyperbola, look at the vertical line and the horizontal line. Oh. And I'm not sure what. I'm drawing the board.
Yeah.
I never learned to read. I'm embarrassed. Okay. Thank you. I might use it. Look at the line, the vertical line. Those are the limiting asymptotes, meaning that hyperbola will keep going on forever, but it will never touch those lines. It will get as close as you want. So will it get 1 gazillionth of a millimeter away from it? Yeah, it will, somewhere way out there, but it will never touch those lines. This is the turn of the hyperbola. This is why space missions are using, like for gravitational assist, from the point of view of Jupiter or whatever planet the spacecraft is going to get in this, it's going to get a turn and whip around. From the point of view of that massive planet like Jupiter, when it sees it coming, it thinks it's a hyperbola, and it'll turn it. And that's the way you turn a spacecraft. Like it's the ecliptic plane is like this, but I want the spacecraft to go around the sun like this. That's a lot of fuel. A lot of fuel to do that, to make it change planes out of the Earth plane. So you send it to Jupiter or whatever in the right way, and it will turn it that way. You get a free boost and a free turn and an inclination change from that. So let's go on to some other things, oddities, riddles, and Gedankenexperiment. Einstein thought that just let's use our mind for some riddles and thinking about things. That was the thought experiment, Gedankenexperiment. And how much time do I have, friend?
You're at about 41 minutes right now.
All right, I can go a little longer, right? Okay. Oh, okay. All right.
I won't notify you.
All right. Let me go back. Here's one. We'll just do this quickly. Using Newtonian physics, if I take picture a train moving, and it's rigid, it's real stiff, and it's rolling on a wheel, and it can go on a straight line or not. And it's going a speed. The center of mass train, here's a line of cars going with all those wheels, steel wheels. So it's racing along. Parts of the train are going the center of mass of the train. The train has a center of mass, and you say, that's the speed of the train, right? What are you talking about other point? Well, it's the speed of the train. But there's parts of the train that are going faster than the center of gravity of the train. Say faster than the train itself, whatever that means. Sometimes twice as fast. Others are going slower, and some parts of the train are not moving at all, as seen from an outside ground observer. And some parts of the train are going backwards. And that's because of something called the instantaneous center of
rotation. If I think this is a train wheel, any motion, like I'm on the rail, at that moment, like the train's going that way, I'm moving that way. As it tilts, this is the center of mass of that wheel. It's going the speed of the train. The top one is going twice as fast as this one, but the train speed is going this speed. This one's going twice that speed, so that's going twice the speed of the train. The one making contact here is not moving at all. If you assume no slippage, it's not slipping or sliding. At that moment, it's zero velocity. Now, as soon as it does move, it rotates, another point takes its place in contact with the rails. So it's like moving another vertical bar. So as I move over here, there's another point of instantaneous rotation. So it's true in inertial space, some parts of the train are zero, going the same speed as the train, and some are going faster. Now, what are train wheels really made of? They have a rim. They're not flat wheels. There's an inner edge and an outer edge. And
that's what's shown in the second diagram. The ones that are below the rail, because it's got an edge below it, at that point, it's going backwards. So there's a lot of points in the train exceeding the speed of the train, and some are going zero, and some are going backwards. That's there. Coriolis force, if you write Newton needed acceleration in his equations, but you start dealing with accelerations in rotating systems, it gets pretty complicated. And one of those terms in there is called Coriolis force, and there was a physicist who studied that. It makes these hurricanes go spin counterclockwise in our northern hemisphere. And so they spin what direction in the southern hemisphere? Clockwise. So that means that the equator,
our hurricanes that start here come to a grinding halt, and then across the equator, they start spinning the other way.
I don't know. I've always wanted to know what happened when that happened. If it crossed the equator, did it stop and then start going in reverse? You know, I don't think that would happen. But the way the Coriolis force is working is what's called the right-hand rule in physics or in engineering. So your thumb is pointing out that's a rotation of the Earth. It's a vector saying omega is how fast the Earth is spinning. The finger is the relative speed moving. It's moving in the rotating system. So that's where I'm going. My other finger is the push sideways. So you can say if that axis pointing upward is like here at the North Pole, and I'm moving away from the North Pole, so what, any direction moving away from the North Pole is moving, going south or whatever. The bent figure,
I feel force. So I'm at the North Pole, and as I walk away, I'll feel something pushing me to the left. I say, oh, okay, well, I'll move. I'll go this way. I'm starting at the North Pole. I move. Something's pushing me to the left. Well, I go this way. I move this way. Something's pushing me to the left. So
think of the heat engine. We're not at the North Pole, but hot water in the Caribbean or North Atlantic, it wants to well up, drawing that heat, and it wants to go upward. Then it wants to spill out radially. That flow of hot air is feeling this. It's feeling a push to the left because of the spin of the Earth and the interplay here of it's called a vector cross product. I'm not afraid to introduce mathematics to you because some of you might be interested in it and pursuing it. All right, train flat car with a live rocket. Let's say somebody stupidly put on a rocket they're transporting on a flat car and it's ignited accidentally. But there was some poor Joe, he's on a ladder or something. He's out here with that ball there's a length there. It could be a ladder, a bar, or whatever, rod, and it's got a frictionless joint attached to the flat car.
Right here. But there's nothing holding us up as this is thrusting, and you see it go by. Wait, it's got to be. What's keeping that guy up there? It's thrusting along. There's going to be any angle.
You put 1 degree or 45 degrees or whatever. What's keeping it up? It's like magic. And that joint down there is frictionless. Turns out when you write all the equations of motion and solve them and get everything, the masses cancel out, and the length of the ladder. I thought, well, the formula has to have L in it. The length. No, it can't. The tangent of that angle is weight over thrust. Just plug that in. Then you solve for theta, and you got the angle. You can get any angle you want. Kind of like levitation. The brachistochrone problem. The mathematicians of Europe were told what the Bernoulli brothers, they made physics of their own contributions, like the Bernoulli equation, named after somebody, I forgot who, but the Bernoulli brothers were very interested in mathematics and all that. They wrote letters to the mathematicians and natural philosophers. What is the shape if I have a ball frictionless? There's no friction whatsoever, and there's a hypothetical blue line. I start at some height, let it go. Of course, it's a gravity field. What curve is it where it gets to the bottom in the fastest time? Galileo looked at it, he goes, experiment. He says, it's got to be a circular shape, he thought. Or is it a straight line like a ramp? And others said, no, that's not working out. So figure it out. Is there one shape that can do it? And the Bernoulli brothers did solve it, but one of them cheated and stole his brother's work, and he tried to publish it, and his brother caught him at it. And finally, the other mathematicians or natural philosophers started coming up with solutions, but it took them like 2 months or weeks and weeks of work. It's called the calculus of variations and the Hamiltonian principle. Okay, Newton got the letter kind of late. He stayed up all night and figured it out in one night. And then he mailed it in to the Bernoulli brothers anonymously. And one of the Bernoulli said, this has the smell of Newton. It's perfect. But Newton was later asked, why didn't you sign it? He says, I don't want to be pestered by those foreign mathematicians. They always question me, and I have to argue with them. I knew I could do it, but I sent it in, and I don't want them to know who did it. Hey, he was just like us, you know. Well, it turns out it's called a cycloid. So if you take a wheel, let a wheel roll along, take a paintbrush, this paint can here. Now I'm going to let it draw on the wall. There's a wall here. Let this move along, and it's painting on a wall. Goes around, and you got to print. I came down here and go up. I get these humpy shapes. It'll go like this and hit a cusp, a sharp point. Let it roll and roll. That's called a cycloid. These are cycloids. I don't need all of them. What the solution is, take one of these and cut it in half, turn it upside down. And it's a solution. It's half of one of those humpy things called cycloids. And it can be proven that it's a minimum energy thing. But it's got another astounding property. If I take whatever, I can put H here, like, well, it's at a height H, and I let it go. Measure the time. It took 1 second or whatever to come down. Okay. What if I put it midway? How much time does it take? Just guess. Is it going to be longer? Or it'd be shorter, maybe? Or Same. Somebody saying the same. All right. Now down at near the bottom, 1/1000th of a millimeter away from the main point. How long will it take? Same. No matter where you put this ball, it'll always take the same amount of time to get to the bottom. No matter where you start. Huh? The very name brachistochrone, chrone means time, like chronometer. That astounded people. Like, wow. Okay, now the seeming singularity. Newton's law, the inverse square law. He didn't say what kind of masses those had to be, but what happens as r approaches zero? In other words, the two particles come closer and closer together. The force is getting greater. I'm dividing by a bigger and bigger number. In fact, as I get arbitrarily close, that F is going to get gigantic beyond any known force whatsoever. So are we talking about two big neutron stars? Or no, he didn't say anything like that. It could be the sun, like I'm saying here. It could be a proton approaching the center of the sun. That's what it says. It's going to have infinite force. So that's a catastrophe. How do we resolve this? Oh, he said, the Pauli exclusion principle, two parts subatomic. No. That's advanced. That's atomic physics of the future. No, we don't need that. So generally, I think he thought of two mass particles or systems of particles that center of mass are coming very close together. But if you analyze just using Newton's laws, you can look at one mass, look at a shell, and there's happy mass in the center, floating or moving around in the center. That gray zone, let's say that's a shell, a spherical shell of uniform density. It's some material's uniform density. I'm going to ask you, when I get close to the, what does happy mass feel as a force from the gravitational pull of that shell? And the happy mass has a mass also. There's an M1 and M2, or the shell is probably gazillions of masses. It's made up of atoms and molecules, or I could chop it up into pieces. And it kind of reminds me of the Dyson sphere. You know, he passed away in 2020. He came up, it was used in Star Trek The Next Generation in one episode. So the Dyson sphere is a shell that captures all the energy of a star, a super technology, you know, are there such things, you know, use all the energy. But if you go back to the, how do we go back? Go
Back button, back up.
Okay, back. I'm going to let it, if I'm near the wall, what do I feel? Do I feel force, no force? What force? Huh?
Zero.
Zero. Okay. Does it make sense?
Like I get caught, I'm feeling all that. I'm so close to that wall. I ought to feel something. Why?
There's more mass on the other side.
Yeah, he's saying. But if I look at the sum total of all the mass, you know it's far away. There's a lot of mass there. So you're right. So when you write, but notionally maybe you can come to that, but when you actually take the rewrite the equations of motion for shells, you can actually use calculus to show the shell inside of a shell is zero. But you can also come up with a formula. The Earth could be infinite number of shells. You could think of the Earth as a shell, and underneath that is another shell, another. So pretend that you've got a tunnel, a tube that's going to the center of the Earth and out the other side. All right. And the tube is made out of some unobtainium super technology stuff. It withholds the pressure and the temperature of the magma and radiation at the center of the Earth. Okay, we got it figured out. You're insulated from that. But what would happen if you were to start at the sea level, drop a mass into that tube? It would obey this equation here. You can actually calculate this using the shells and the theorems and all that. It's the rate of change is the acceleration of that mass. That's like the MA here, plus KR. That's the radius away from the zero. R0 is the center of the Earth, and R is out to the mass. In my field, in structural dynamics and vibration, that's the spring equation. It describes what's going on with a spring. Any mathematician can look at this, and in our field, we don't have to solve this. We can just say, oh, that's the spring equation. That's the oscillation equation. We don't have to plug in numbers or anything. That's another point I'd love about mathematics and things. Sometimes mathematics and physics, you don't have to plug in the numbers. You say, oh, it does this. It has this characteristic, or it has a period. It speaks the way it behaves. The K is a function of pi, G, rho, the density, and the little m. When you actually try to evaluate it, at r equals 0, the velocity, when you drop a particle to a tube, it reaches a maximum velocity in that square root. Hey, we saw that before a few slides back. That's orbital speed.
If you're at sea level, you're capital R way up to here, let's say there's no air drag, the atmosphere is gone, and the Earth is smooth plain, all the mountains have been sanded down, smooth, or it's an ocean. You would orbit, if R is from here to here, you would orbit at that speed.
That's where it says V max. We saw that equation before. But that's also the speed you get at the center of the Earth. You started from 0 at sea level, and it's picking up speed. When it gets to the center of it, it's going over its speed. Here's the beauty of it.
Take this, I'm moving my finger at that speed. Okay, I can do it this way. Going that speed, orbit speed, that's what keeps it in orbit. Now, take a flashlight, or up here, turn it sideways, look at my finger going down and goes up. That oscillation, my finger shadow is going to go up and down and up and down. That's me falling to the center of the Earth. So it's just like taking a circular orbit, turning its edge on and projecting it onto a screen. And it'll oscillate forever, as long as you don't put in other forces like drag and magnetic forces and stuff like that. All right. Oops. Not yet. Backspace. Oh, this is my last topic here. I was intrigued by this equation right here. The spring. So what kind of orbit, if you were inside that shell here? Let's say I'm inside of a bunch of shells and they're made out of dark matter. What's one of the properties of dark matter? Well, it has gravity, but they register on no sensors. They don't collide with ordinary matter, baryon matter. They don't collide at all. I don't get any measurement or flashes of light or forces or nothing. There's nothing except the gravitational pull. So what if I'm immersed in a swarm of hornets called dark gravity? Right now, there's dark matter in this room. There's swarms of it. You don't see it, you don't feel it, but the gravity's there. Well, so what if I had a lot of it? What orbit would it take, say, with respect to the center of these shells of dark matter? What I got was constant angular velocity. In other words, it's not Keplerian. Kepler's law says it varies with the square root of 1 over r. The closer I am to the sun, it says Mercury goes around faster and faster. Venus goes slower. Earth goes slower still. Pluto's going pretty slow. The comets way out there in the Oort clouds, they're going super slow. That's Keplerian. But when I immerse myself in dark matter, and that's all I have constant angular rate. That means that wherever these circles are, like that's the center of the galaxy or whatever, they're all going at the same. If I'm rotating this wheel at a rate, they don't obey Kepler's law. It's deviating from it. In fact, that means the further away you are, the faster they're going. They're going that celestial line. Oh, that makes no sense. Or the clusters of galaxies, they're going too fast. It's as if they're inside of some swarm. Yes?
So if you drop a marble in that tube that's going through the center of the Earth, why doesn't the marble just stop at the center when all the forces are at equilibrium? Gravitational force.
That's a good question. It says there's no force there from the gravity because it's only the inner shell, the inner body that has the spring equation says I've got maximum force. As I go in, the force is getting less and less and less. It's like a spring relaxing. Like I have a tension spring, it's relaxing, but it goes the other way. It's like
is that because of the speed you reached?
But when you reach the center of that speed, if you're going to stop, something has to stop you.
Yeah, okay. So it's a momentum that carries it back.
Yes.
Okay.
That speed, it just coasts on through because there's no opposing force. So it's as if it's a double spring. So I've got a spring on a marble, one spring here and one here. When I pulled it over here to one side of the Earth, one spring has maximum tension. The other one is compressed. When I let it go, when it gets to the center of the Earth, both springs are relaxed. There's no force. but it's got that speed. So it's going to compress the other string and stretch the other one.
So if I had a very long pole, half the diameter of the Earth, and I lowered the marble down and then released it, it would just stay where it is.
Yes.
Okay.
And of course, in that movie with James Mason, Journey to the Center of the Earth, they should have been floating. There shouldn't have been an ocean at the center of the Earth. The dinosaurs should have been floating there too, and all the sea creatures and stuff, and all those weird. They should have been. But in the movie, it says we've reached the center of the Earth where the magnetic field attracts gold. That's a line from the movie. I didn't know magnetic fields attracted gold, but the movie says it did. So a lot of people have watched it, so it's got to be true. That was a lot. Die questions, hay preguntas de ustedes. Einige Fragen. Habt ihr einige Fragen? Ja.
Rodney, I don't pretend to understand any of this.
I pretend.
Yeah, you did a good job. But in more current science, they say that the galaxies are speeding up, they're flying away from each other, but they're not changing their velocity inside of themselves. It seems to me there's a clue in here for what's going on.
Sure. And I welcome those ideas. I just read an article in Scientific American. There are thousands of papers coming out about the explanations for dark energy, dark matter. But what's missing is they're all elegant. They have unpronounceable long titles. They're not proposing experiments. The article was about, all right, you guys are, everybody's smart with their elegant math. Where are your experiments? It's hard. So I think we'll get there. It's just hard right now, very difficult. So what you're talking about is the stretching of space-time. And we don't know if that stops or comes to a stop, and it comes back to the big crunch instead of the expansion. We don't know yet. Nobody knows. Yes, sir.
I've always had a lot of trouble with the tire rolling down the road at 60 miles an hour. And in my head, the only way I can come to any comfort is that the angular velocity for each point of rubber on the tire, they're all the same because it's rotating at a constant speed.
From the viewpoint of your car.
Constant angular velocity.
From the viewpoint of your car, yes.
Well, the rubber itself and what it's feeling, because it's not stretching at the top and compressing at the bottom.
The tires really do deform at the bottom.
Yeah, I know.
Yeah.
But that's because of the weight. But if you had a weightless car and you're just rotating that fast. So when you go to talking about the top moving twice as fast as the bottom, well, yeah, for a point in time, the bottom tire at a single point has to be at zero speed and the top.
Right. That's why it's called instantaneous center of rotation.
But isn't that sort of a useless concept? I mean, what do you ever do with it? Because it's not real.
Well, it is real in inertial space, and it's taught in dynamics for students, not just the train wheel, but there is a search for rotating bodies called instantaneous center of rotation. There's a lot of homework problems in it too, because I taught at Rice and that was one of the things that came up with. But you're right, it's an instantaneous center. An instant later, it's another point that it's rotating about. Okay, not so much use for the train wheel example, but it does illustrate there's pieces of matter or molecules that are going faster than the train and others going slower than the train. That's the concept that leads to that. And also that some points are going the other way. Now, on the train, it doesn't look that way. What I was saying was for an inertial observer, you're fixed to the ground. You're a ground observer. When you're looking at it go by. And Newton requires inertial frames, non-accelerating. He needs for these equations written in stationary frames. When you're on the train and whirling around, these equations don't work as well. You got to do all these transformations. But anyway, okay, that's a good point. Yeah, it's esoteric and illustrative. I hope you, some of you that are young enough are considering advancing your education in physics and math and all that. The reason I did is I was interested in everything, but the power of mathematics, to me, it's the language of the universe. It's beyond magic languages. My niece is wanting to, she writes novels about sorcerers and all this. I said, the language of the universe is mathematical physics. It's hard. It's another language, but it predicts things that never were known before. It predicts experiments, and it leads to technologies that never existed before. And magic has a hard time doing that. I can only, when I wish for the genie to do something, it'll only do stuff I already understand. So mathematics goes way beyond that link to physics. Thank you.
And by the way, these are the tools we use when I was in school. I didn't use this one. And they work after a Road Warrior event, or Mad Max, Blade Runner, Apocalypse, or whatever, or nuclear war. They still have precision and they work. And you don't have to expose them to sunlight or anything. They'll work thousands of years from now with the same precision.
All right, Rodney, thank you very much for that really cool presentation. I enjoyed that. Okay, so Ron, would you like to tell us, say a few words about the DVD library?
Yeah, if you've been here some time, feel free to take them out. We've got 200 DVDs. Just a warning that when they're marked IC, there's 80% of them that's from Astronomy Magazine. And it'll say whether it's Discovery or whatever. And then we also have a lot of the great courses also. And those are like, 10 hours plus long, so be aware. We also have pocket atlases, planispheres, moon maps, all on loan. Thank you.
Okay, so during the break, you guys can walk to the DVD library and take one of those out online. All right, so after the meeting, we're going together Mod Pizza. It's the one up right in front of HEB. You shoot up Middlebrook, go left on Coast City Boulevard, and right past El Dorado. There's a Mod Pizza right in front of HEB. We'll get together and have discussions about all variety of topics. All right, so we're going to take a short 10-minute break, and then we will get back together for the second part of our meeting, which is going to be really short. 10 minutes. our meeting.
Interesting.
Okay.
Brandon
thank you.
has-
I don't know
Ron
anybody.
muted us, so you didn't have to listen. Okay, so we're gonna get started. Second half of our meeting.
It's like Asbury flying the
Yeah,
ball.
there should be a couple hundred.
Extra premium on that?
I don't have the cowbell tonight. Sorry. That was a really good presentation, wasn't it, Ron?
Oh, well, thank you.
Hey,
I
Brandon.
hope people, the young ones here, think about pursuing physics and math.
That's right. You'd be really cool like Rodney. All righty. Okay, nano VNA. Does anybody in this room know what a nano VNA is?
I do.
Oh, you do? Oh, you do. Carrie, you know.
I went in the car. Right?
Oh, no, really? Okay, okay. Anybody else? Nobody else. Okay.
Same place you went.
All right. Now, I know that many of you are, I'm driving you crazy with my radio astronomy stuff, but I know some of you are really think this is cool. So so this is going to be quick, members met. But some of us have taken an interest in radio astronomy. And this is a little gadget. It's called a nano VNA. And I learned about it. Carrie's probably known about it for how many years? How many years about
I've
this?
had it for 2-3 years at least.
See, he should be up here doing the presentation. So 2 or 3 years. I've had one for about a month. Anyway, so somebody on the Facebook Amateur Radio Astronomy group turned me onto this thing. It costs like, it's a little less than $100 on Amazon right now. And basically what this is a little gadget that you can use to hook up to your radio telescope, your antennas, and test them and figure out whether they're going to work or not. Because, you know, usually we just make this antenna, we point up in space and we say, gee, did I get anything or not? But this is a really cool device because you can actually use this to test your antennas to see how well they're going to perform. You can do this in your house. It's a piece of test equipment for antennas. So in our case, we're doing radio astronomy. Here's an example. Here's 2 different loop antennas. This one on the left here is my first implementation. This is all for measuring 21 centimeter neutral hydrogen in our galaxy that I've been talking to you about recently. And I've made a whole bunch of different antenna feeds. And this is called a loop antenna. You can tell why it's got a nice little loop here. But the one on the left, they look almost exactly the same. This is a Cape pan, yes, 6-inch Cape pan. And this loop on both of these is 21 centimeters, which is the wavelength of neutral hydrogen. But the difference on this one, you can see these 2 little wires that go from the loop down. The wires are there, but on this one here, it has a coaxial feed. There's a coax that goes all the way up here, and then it goes around like this. See? That's the difference between these 2 designs. One is just wires, and then one has a coaxial feed. And you may think, hey, that's going to be no big deal, but you're going to find it did make a difference. Now, using my nano VNA, I can actually test this thing to find out. So before I had the nano VNA, I made this antenna over here. I was trying to use it. It was getting okay. I was getting some kind of signal, but not really that great of a signal. But with the nano VNA, I was able to design this new antenna and test it. And I'm going to show you that this gave me much better results. So this is a screenshot from the nano VNA. The one on the left, these are the 2 parameters that we'll talk about tonight. One is standing wave ratio, and one is optimal. That's what you want. You want to get to the closest to the number 1 as you can. And in radiation resistance, we'd like it to be 50. But the original design, the SWR, standing wave ratio, actually was 6.8. And it's up here. It's actually that little blue dot. It's actually off the screen. It's so bad. And then the radiation resistance was 68.14, which is the green one down here. But with the new design, the only difference was running wires versus the coaxial feed. This one over here gave us a standing wave ratio of 1.3 and then a radiation resistance of 55. So the SWR is here. See, it's wave curved very nicely down here. And the radiation resistance down here, the green one, is close to 50 ohms. Okay, so that's testing with the nano VNA. Now, this is some results actually looking at the hydrogen in our galaxy. So these are both at 46 degrees declination, and I'm looking at these peaks of our neutral hydrogen in our galaxy. And with the old implementation, I was only able to get about 1.09 dB signal noise ratio. But with the new implementation, and by the way of using the nano VNA to actually be able to test and design the antenna, I was able to get the 2.06 dB signal noise ratio, which is a pretty good improvement. So you guys that are interested in radio astronomy, instead of just pointing it up in the sky and just trying to see, hey, did I get a signal or not? This is a way you can actually design your antennas and actually test them in your house to see if your antenna is doing what you think it's what you want it to do. And you can see all my projects on my webpage, just like I tell you all the time, hollandobservatory.net, and that's that. Any questions about nano VNA? What?
Which hump is the hydrogen signal on the graph?
Okay. John, you haven't been here for a while, have you? You've been gone, haven't you?
Yeah.
Okay. I've been driving like crazy with my radio astronomy stuff for the last few months. Okay. And I look out in the audience, some people are like, oh, and some people are thinking like, oh, this is the coolest thing ever. So, it's like I got a real mixed response to this thing. Okay. So, John, here's what's going on. This is, okay, 1420.4058 is actually neutral hydrogen, which is going to be right around.
Where's the big wide hump?
Yeah, right here. That's where the neutral hydrogen would be in the lab. If we could do it in the lab, 1420.4058. Okay, but what's going on is the neutral hydrogen is spread out for a couple of reasons. One is there's thermal, it's moving around because the thermal energy is going back and forth because of that, and because different parts of the Milky Way, when I'm looking at this arm, it actually has different velocities. What these different frequencies correspond to different velocities of the neutral hydrogen. But what's really cool about this right here is these two other humps here, which everyone's going to say about a million times now. This is evidence that there's multiple arms in the Milky Way. So you can actually go out in your backyard, and this is how you can verify and test that the Milky Way has a multiple arm spiral galaxy. Because this is the arm that we're in here, but then these are two other arms beyond the one that we are.
Oh, so different redshifts.
Yes, different. And this is actually blue shifted. These are redshift and blue shift, exactly right. But we're going to higher frequency. This frequency, not wavelength.
Oh, this frequency.
Yeah, frequency. So higher frequency, shorter wavelength, and so these guys are actually coming at us. Now, when you look at different declinations, you're going to see some areas where the stuff's redshifted and it's going away from you. But there's in other declinations, you're going to see it where it's actually coming towards you. It depends on where you point your radio telescope, what declination you're at.
What's the sharp spike?
The sharp spike is some man-made thing.
Okay.
Anytime you see some sharp spike, it's a man-made thing, or it's a eureka thing. I discovered something really wonderful.
Microwave.
Somebody turn off the microwave oven. But I got to tell you, this is a clean signal. If you saw my Wi-Fi antenna version of this thing, it's got trash all over. Please look at it on my webpage. It's got trash all over the place. But if look at my webpage, you can see when I got this 7-foot dish in the backyard right now I made, and it's actually working really well. It's really clean, and I'm really happy with it. But look at my webpage or look at past presentations. But yeah, and Trevor came over and saw it actually in person. He's the only person that's actually seen it. Does that answer your question?
Yep.
It's really cool because if you tell me you can go out in your backyard and measure our Milky Way from your backyard, you can figure out how far we are from the center of the galaxy. You can figure out how many arms there are.
Yeah.
You can figure out the rotation rate of the galaxy. You can do all this stuff, just by measuring the neutral hydrogen. You can actually make a map of the galaxy this way too. So it's pretty cool, I think. Any other questions or comments about this topic? I just love you guys say something.
I don't know a lot about astronomy, but did you measure hydrogen trajectories from the far side of the galaxy with the cake pan?
Yes.
Okay. With the cake pan.
And I paid like $5 for that cake pan.
That's a special cake pan.
It's a special.
It's very special cake pan.
Okay. I can't resist, Timothy. I got to tell you this. Okay, listen. All right. So when I was looking at this, I was reading about other people's experiences with these cake pans, and so there's people who are having trouble with their antennas, and they're saying, "Oh gosh, what's the name of it? Wilton? Does somebody know? Wilson? What? Wilton. Yes. Okay. So the Wilton cake pans are the good cake pans, right? But what happens is some people made these antennas out of the cheap ones. They got at Hobby Lobby or Target or someplace like that, and they're actually having problems with them working as an antenna properly. And the people who made cakes with them were complaining because the cakes weren't cooking evenly. They were cooking like hotter on one side and they were uncooked on the other side. So the cake people were complaining about these crummy cake pans. And the radio astronomers complaining about because they wouldn't work as an antenna too. The same ones. And so they all agreed that the Wilson Cape pans were the best ones for cooking cakes and for making telescopes out of.
Okay.
I thought that was hilarious. Anyway, my wife knew all about the Wilson Cape pan. I didn't, oh, those are the good ones. Does that answer your question? Kind of. Okay, but Timothy, I think what you're trying to get to is you can make stuff, not a regular telescope you'll learn, but a radio telescope you can make out of a lot of, junky looking things, because like when you make a mirror, it's got to be perfect. It's got to be grounded, it's very precise. Your radio telescope can be all over the place because the wavelength is so long. It can be really sloppy, and the thing will still work pretty good.
I thought it had to be like a perfect parabola. I didn't realize.
Mine is a parabola in the gross sense of the word. It has the general shape of a parabola, but it's made out. It's got waves and bumps and all kinds of stuff because the wavelength is so long, 21 centimeters. Even if I was off by 1 centimeter, that's like a 20th wave parabola. So I can be pretty far off and still the thing will work great. If you have a 20th wave mirror and a telescope, you're doing really good. So my parabola, as long as I got within a centimeter, I've got a really great parabola. It's all wavelength dependent. What? Yes. But if you're interested in radio astronomy, it's really cool. So, any other questions or comments about this? Okay, I just love the variety of interest. Brandon.
What's the significance of 46 degrees as declination?
The significance is there's a big tree right next to it. and okay, I made this thing is really heavy, Brandon. I mean, I'm guessing it weighs about 80 pounds, the dish itself. And I put it up there myself. I was carrying it I felt like Atlas, carrying this thing out of the garage and trying to put it on this thing. I thought about asking somebody to come over and help me, but I'm too embarrassed to do that. So I put this counterweight. It's got a low Sandy counterweight on. Look at my webpage, there's a picture. It's got a low Sandy counterweight. So when you point the thing straight up with the low Sandy counterweight pointing out, it just happens to be about 46 degrees declination. I need to work on it so I can move it to more different parts of the sky, but there's a tree over here and the counterweight isn't very adjustable. But no, that's not the best. That's not the best place to point it for. But it is kind of cool because you can actually see 3 humps there at 46 degrees.
Yep. Okay.
Charlie.
Is there an integration time you have to do to get this? I mean, how long you have to stare at the sky to pick this up?
I am so glad you asked that. So glad. Okay. So, when you take pictures, like, I do astrophotography, you probably realize that by now. So when we take pictures of the sky, we might take 10 or 20 or something pictures, and we combine them together to make a pretty good picture out of it. All right. These samples are 902,000 samples.
Okay.
Oh my goodness. Yeah. So each one, if you look at my spectrometer, like you look at the live data, it's like a bunch of garbage. You can't. It doesn't look like anything. But what I'm doing is I'm dynamically averaging together 902,000 all the time to make one of these.
Okay.
Yes. It's very, very dirty. It's very, 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 very dirty.
And so how long does it take you to do that?
The 902,000 on mine takes about anywhere between 7 and 12 minutes for each sample, because depending on how good my Wi-Fi is working, because I'm not sitting out in the backyard, it's got a Raspberry Pi sitting out in the backyard, and I'm controlling this from inside the house. And so depending on how good my Wi-Fi reception is, it can be arranged.
How long does it take to compute the averaging of the samples when it's done measuring?
What?
How long does it take to compute the averaging of all the samples?
About 7 to 12 minutes.
Oh, that's what you're talking about. Taking a whole picture.
Well, each have a processing time. Is this, you do a post-processing,
no,
integrate all that?
This is actually live.
Yeah.
It's actually done live, and it's about 7 to 12 minutes for each sample I take.
Okay, so that's where that time comes from.
Right, but if you're talking about astrophotography, a bunch of us in here are astrophotographers too. That can take your whole life. It takes days to process an image. Yeah. Is that what you're asking?
Yeah, it is.
Okay. All right. Anybody else? I'm so glad you guys are interested in this. I thought you guys were running out of here. Okay, anybody else got a question about this? All right, fine. I'll try not to do a radio astronomy thing this month, I promise.
Radio astronomers need to be heard too.
What?
Radio astronomers need to be heard too.
Yeah, I know. Okay, so David's not here tonight. Star Party News. This is going to be the shortest Star Party News you've ever seen. There it is. We have one event on February 23rd, Friday at Evelyn Meadow Library. The time should be determined, full moon. David says it's not his planning. And then at Hack Winery, there's 8 events in planning for next year. And that is our entire Star Party News. Hope you guys can come out to Evelyn Meadow. We had a really good turnout last time we were there. A lot of people from Seabrook and
Hey, Doug, Festivus 2022.
what?
Oh, 2024.
Titles 2022.
You know, I didn't make it. You know who our Star Party chairman is, right? Okay.
Where is the Metro Library?
It's in Seabrook.
Okay.
It's, you know where Meyer Boulevard is in Seabrook by chance?
Probably do, but.
Okay, 146.
On the other side of 140, on
Yeah.
the other side of 140.
Yeah, War side 146.
All right.
Yeah.
And it's,
Oh, I know. Is it near Seabrook Intermediate?
Yeah.
Yeah, okay.
Yes, across the
almost
street.
across the street.
Yeah.
Yeah, across the street.
You can use it over there.
Yeah, really nice
I
library.
remember that now.
Yeah. And last time we did, we had all kinds. We had little kids, we had people in wheelchairs, we had all kinds of patrons from the library. They really loved it. So. Okay, there's David's joke for tonight.
Oh.
Again, you know who our Star Party chairman is. Don't blame me for this. Okay, door prizes. Donations are needed, guys. So if you guys have anything astronomy related you'd like to donate for door prizes, please do that. Otherwise, look at your tickets. Okay, ending in 926.
Did you actually?
All right, first time, come on down here. Okay, so for you, I have a moon map, or I have a stargazing notebook. You can use all your stargazing, or I have these little planet pins, they're like pins you put on yourself with planets. Or I think, Rick, did you bring this?
Yeah,
STS
I brought a whole bunch of stuff.
I saw that. STS-106 images from the space shuttle mission STS-106. What?
The CD.
Gee, all right. Very good. Thank you. Yeah, all right. All righty. That one says 930.
Say 930?
Are you holding your hand up?
Yeah.
Oh, Chris, come on down here. Oh, now, Chris, wait a minute. I have this decal. It says, I am an astronomer. What is your superpower?
I love it.
You want that?
I don't want to. That's perfect. Thank you so much.
Yay. All right, Chris, our vice president. Okay, one more. Oh, man. 920.
That's us. What do you want?
Is that you? All right, come on down here. I got is that Ed Grafton there? Oh my goodness, he came back. I can't believe it.
He wants to do that.
Okay, moon map. Oh, stargazing notebook.
You want the moon map?
Yeah.
What's the moon map?
It's that bright white thing up in the sky, Ed. I don't know if you've seen it or not. Ed's actually like a writes articles, I think, for Sky and Telescope, so I'm surprised he came back, but there he is. Okay. All right. So next meeting is February 9th here. Are you trying to tell me something now?
Yeah, if people want to get on the email list.
You already talked about that.
I didn't hear them.
Okay, yeah, if you guys want to get on the email list, go grab one of those tear-offs up there from that clipboard that Al was just waving around. Yeah, if you don't get our email distribution. Okay, February 9th here at UH Clear Lake. We don't have a speaker yet. We're going to try to figure it out. And hopefully we'll see all you guys at Mod Pizza directly afterwards. Thank you for coming.